as motivation, in the sugar-beet production, leaf disease is one of the big problems because there is a high pro yield loss caused by such a disease, especially some fungus, can cause even up to 50% sugar yield loss. And this is a big problem. And to control this in a sustainable way, there are actually some rules that in Europe um, have been given in the last years, I guess since 2014. And these rules or these principles says that to control such as diseases, there are three aspects. First, the cultural practices, including crop rotation, for example. A second aspect is the use of resistant and intolerant cultivars against such diseases. And as a last measure or last barrier is plant protection, the last aspect that have to be taken into account. For these two last aspects, the use of cultivars and the, ident the identification of cultural of resistant genotypes, and for the plant protection, you requires disease quantification. So there are experts that goes into the field, collect some disease parameters, and take a decision. And maybe this is one of the principal aspects that requires automation, an automatic approach. And here's what I actually work on my PhD. Parallel to this, and as we know, such many years there was a big development of UAVs as a platform to take off with developing cameras. And as you know, cameras have been developed in resolution, but also in spectral range with high capacity, high quality, nice radiometrical quality have been developed in the last years. And with the development also parallel of the drones, it's possible to monitor huge areas of the kind of big areas of fields. And nevertheless, it's the question what to do with this collected data, and this is what we focus basing this approach of disease quantification to deliver actually mainly two of these important disease quantification parameters. These two parameters are actually disease severity, more important for the breeding aspect, and disease incidence important for the second aspect, which is crop protection. When we start my PhD, we actually firstly collect data for the first years, and we try to use the approach that our colleagues already developed, also in the University of Bonn, especially. We focus on the work from Dr. Lottes, and we make some cooperations with them. We take the pipeline for detection of plants and plant center, and our idea was to adapt to our problematics, variety trials, for example, and we try to see some aspect like optimization in that way. When we detect our scoring unit, which is quite important for disease quantification, we try to perform the severity. We focus on one reference approach, which actually breeders use, the so-called KWS scale, to quantify yeah, how much damage the pathogen have been done in plants. We realized that we need to improve, and that a big potential will be if we switch our approach to a pixel-wise classification, because they will give us the chance with most post-processing aspect to take out more and different parameters for disease quantification, and also seeing this approach of applying a pipeline for delivering indicator in the crop protection aspect. We realized in the middle that something is more important, something important aspect have to be taken into account, which was the identification of a scoring unit. And then we see, okay, for leaf diseases, maybe the segmentation of leaves is one important aspect that we take into account. And then we focus and also inspired and the work of CP1 um, with that to our plant disease perspective, and we try to see some optimization at that point. And finally, when we took an approach that we can extract different disease quantification approach, we try to apply it and in the demonstrator for of aiming site-specific application, the reduction of fungicides into the field. So I will go into through this story, and I will start with the first point or the first publication. As we mentioned before, we take the approach for our colleagues from Philip Lottes, and we try to see um, some aspects, like for example the timing when we have to make this plant detection, at which growing stage should be better. One important aspect to see in variety trials that the distance in the row between the plants change, and what should be the optimal distance between these plots. This aspect we try to clarify it in one publication that we make, which is actually mentioned here. And in the results, we observed that the optimal conditions for quantification was like when the plants have at least 6 to 8 leaves into the canopy. The optimal distance between in the row should be 20 to 21 centimeters. Um, we also observe some underestimation, which approximately we can't, yeah, at approximately 5 plants less that our reference, and we observed that one of the principal aspects for this underestimation is when the neighbor plants are close together, and specifically with the low inter-row distance. So leaves comes together and midribs overlaps with the neighbor plants, and neighbor plants are counted as one. So it's one of the principal aspects that keeps us in slightly deviation from our reference numbers. When we detect when have to fly, we save, and you already know the work from Maurice Gunther and Facundus Pisua, which was was the inspiration of this plant cataloging. Then we georeference the plant-centered. We come into this second aspect, which the quantification of the estimation of the damage. This time, as I mentioned before, we take a scale, a diagram, a categorical diagram that goes from 1 to 9, proposed by the KWS for the references. In the results, we can observe something interesting, which was that the collected data during the vegetation periods were totally imbalanced. Um, from the reference data sets or the training data sets, the most frequently yeah, reference data was with this case 1 when they were totally healthy, or 9 when they totally disrupted. Here's an image, looks like plant within a scale of 9. Um, we also learned that the best performance are with these two classes, with the most frequently classes. We observe some low performance with the F1 scores between classes 2 and 7, which give us to came into the discussion that probably this performance, because we have a lot of classes, 9 classes, lead us to a low interclass precision, which is related to a limited separability between the classes. And we observe in the literature, for example, that this is one of the principal aspects to, or the principal indication to reduce the number of classes. Well, if we reduce the number of classes, this is for us a disadvantage, because we uh, diminish the granularity of the disease severity, and this take it take us take us out the ability to discern between different resistance level, which is a disadvantage for the plant breeding scenario. We also say if we see that the pipeline can be applied for a plant protection aspect, we say that at that point or at that time, our precision of the class 2, which was the first appearance of leaf diseases, was the precision quite low. And this was approximately 15%, and which tell us that probably we should not be the best approach for also plant protection aspect. We came also into the literature, and for example, already in the 80s, Kranz mentioned that yeah, a diagram or a three-dimensional diagram, when you have a plant, you quantify the disease severity in a three-dimensional way is um is um is maybe very disadvantaged even for the references when the expert goes into the field to estimate a categorical aspect in a three-dimensional plant. uh, gives you less accuracy or less precision for the estimator. So you have also an error related to the experts or an error related to the ground truth, which should be an advantage. So what was at that time his suggestion, make the scoring unit or the references as simple as possible. And he always mentioned if you have a plant and you have a leaf disease, for example, segmentate the leaves and quantify the leaves. If you have a root disease, take out the plant and quantify the root. So make it as simple as possible to have more robust reference data. So this motivation, or maybe this at that point we decide to switch to another approach, to the pixel-wise approach. And here's an overview because we didn't know how to make the scoring. So we propose to first between a plot define some instances, and this time circular instances. Here in the graph we can see how was defined, and our idea was to make yeah, classification of each pixel based in the spectral data and the multispectral data. So we have 5 channels that can help us to differentiate between diseased, healthy, soil, and other class. We also propose to change in that point, to change uh, because we have the number of pixels from a categorical right now to a ratio scale disease severity quantification of diseased area. Um, we also wanted to take one output from the photogrammetry, from the structure for motion. This is the digital surface model. We wanted to adapt in this processing step, take out this slope output, which is a transformation of the digital surface model, and calculate surface parameters. And this is why we want to adapt area-based parameters. Well, from the results of that point of the research, we also observed the same aspect that with the plant counting, and that we have unbalanced data. Here in the graph, we can see in the side A that many pixels are were collected from healthy tissue. Just few pixels were related to diseased areas. A lot of information also related to soil areas, and just few to other objects that we couldn't roll. What one interesting aspect is also that many of this information is related to severe symptoms, and just few for the first symptoms. So this can also be important for the detection of the first spots during the classification. We observed that by classifying um, machine learning approach, we didn't use at that point such a complicated classification of person. We didn't use deep learning, more machine learning at that point, PLS, D, and subprobect to machine were the classifiers that we choose at that time. And we observed that the healthy class, which was for the performance quite good classifier and precision and recall, really good F1 score. Nevertheless, here important, the disease class present still a very low precision, a better recall than that we can put can get. Um, uh, we observe by performing the post-processing and comparing the reference data with the UAV data that we have for this parameter. This is actually quite important for the plant breeding. This is severity. We have nice correlation, less sensitivity at the beginning, but really good correlation. We also plotted over the time these curves, and they show similar behavior, a bit underestimation, but this is shouldn't be a problem. The most important aspect is that there is a linear relationship between these two parameters. We also could apply, which is parameter quite important for the quantification of the progress of a disease, the AUDPC curve, and we compare this parameter, which is actually an integrated value of this disease severity curve over the time, that we get the same results from the linear modeling, which the expert and also with the UAV data, which was for us quite important. We also could calculate additional UAV parameters. A huge list we publish also in this manuscript. We firstly calculate from image basis the parameters that requires for the crop protection, the disease incidence, and in the discussions of that point, we just observed that we can describe the behavior of the disease with these post-processing parameters, for example, the number of clusters between instance or the number of spots between an instance and the mean area of these spots. We have a small example, the description, for example, the steeply increase of the number of spots during the disease development was described, and then also an increase of the area of these spots. Well, this behavior was actually also described in some literature in 2004 by Violent Cook, and now we can, with the UAV right now, show it with numbers, which was quite nice to see. Um, we also observed that should be another parameters important for the prime breeding, and that are calculated with UAV, that shows even more differentiation between the different genotypes, which were the area of the foliage, the area of the healthy tissue, and also the mean area of the clusters between an instance, which is quite interesting. That probably, yeah, this automatic quantification of disease gives you more potential also from the differentiation of Cercospora or CLS resistance. But how about the crop protection scenario? How about the performance of disease incidence? So we plot also the curve of this automated approach, of this UAV approach, and we observed one important phenomenon, that during the time series development, a high value of disease incidence is observed even when the disease was not there. So something wrong was happening with the performance. One in this was, for example, the foliage cover over the time. And one important aspect is that when we have less less foliage cover, the chance that we get higher wrong classification or wrong estimation of disease units were high. When we go into the image, we can observe this wrong classification were mainly based in two aspects: when there is still some bare soil recorded by the UAVs, vegetation rest, and because we just observe the spectral value of the pixels, are also quantified as disease areas, especially plant debris, but also some ages of the leaves were also quantified as diseased pixels, and this leads you with the circles that you define one circle or as a diseased unit. And this gives you at the end the consequences that you make a wrong classification of the diseased scored plots, and you have a higher, yeah, false positive quantification of wrong disease incidence parameter. So what should be the solution at that point to reduce this number of false positive classification? Maybe should be the segmentation or giving not the chance of this extraction of parameters to quantify the disease. In that case, we observe that, yeah, leaf segmentation should be a possible solution because we are we have not the chance to quantify in a pixel-wise the soil, and we can even deliver also this disease development, yeah, with the automatic scoring. And this was the motivation to switch to the next step, and also we observe a lot of works from CP1, and we say, okay, maybe we have to oppose with this leaf segmentation, this time adapted to the, yeah, plant disease approach, and we have to make some modifications. And in that case, the plants are quality development. We need to classify our leaf segmentation approach that segment the leaves when you have foliar canopy closure. Also, another aspect have to be taken into account is the disease progress and the senescence. So leaves are changing also in form and color, and this have to take into account for the leaf segmentation. As I mentioned before, our main motivation was to deliver this disease incidence and to reduce this false positive rate. Um, yeah, we oppose, and you know very well, this instant segmentation approach matters in the end. And as you know, one of the principal challenges is to deliver a training set. A high number of label images are required in that case. And when you have a lot of dynamic, especially this factor of disease, but also when you fly with a UAV, you have these light conditions aspects. You need to somehow label a lot of images, and this is, manpower for labeling is one of the principal limitants and web posts for the data augmentation. Not that developed approaches, but we focus more on standard techniques like rotation, flip, zoom to increase our data sets, but also we focus in this copy paste approach by segmenting leaves and selected a list of backgrounds and creating these artificial images for the instant segmentation. We want to take in our performance this UAV and also disease aspect. So we try to balance at different disease development stages and with different light conditions our test and training set. And our main idea at that point was also to transfer this post-processing aspect from the circle to the leaves for the disease quantification in a later steps. Yeah, and at the end we wanted to evaluate if the leaf-based if the disease is based on the leaf segmentation, yeah, the adequate form should be for crop protection. And the results, and I didn't, because of time, I didn't show a lot of our design, but it was published this point. With we have different strategies, and here is in a table of the different strategies that we take. For example, strategy one was the strategy with only artificial images or copy paste images. Strategy five was an approach with only data or images augmented with standard augmentation techniques, and we observed that the average precision increase um, according 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 with strategy 2, 3, and 4. They have a mixed number of artificial images and standard images, and the best performer was observed actually when we only had standard augmentation techniques in that case. By observing this classifier, we observe in the test set, we try to make some clusters, some groups according, the disease progress, healthy, middle, severe, and also the like conditions. And then we observe that this classifier is actually quite constant, but segmented disease leaves that are healthy, middle, and or severe affected. But also we observe that the leaf segmentation, classifier have some disadvantages under sunlight conditions. Also here there is a clear decrease of the average precision. We could adapt also the post-processing step from the circle instances to the leaf segmentation instances. We get also some new parameters like we have the leaf segmentation, and we also have the area with the digital elevation model, so we could calculate the leaf area, but also the slope, which is also a parameter from transformation of the digital surface model. And all the parameters that we calculate for the cycles, we can also adapt into these leaves instances. Something interesting in the results, and this was something that we didn't expect actually, that this parameter important for the plant breeding. When we segmentate, by leaves, they decrease the performance. So the correlation is loose. In that case, when we make the segmentation of in a leaf form, um, here, one important explanation is the disease development, and this is why, because of probably the nadir perspective of the UAV monitoring, we are only recording healthy plants, and when some disease development aspect appears, and sugar beets have an interesting strategy that used to catch sunlight when all the canopy was disrupted. Start producing new leaves and or developing new leaves. So uh, disrupted leaves are laying down, and new leaves are in the upper part. So if we are flying with the drones, we're probably recording this healthy lips, and this makes the effect that when we can observe, of the expert can observe all the leaves stages, the drone can only observe the healthy leaves, and therefore here this parabolic behavior. Interesting approach for the leaf segmentation, and this is something as mentioned before that what didn't expect. Um, But we also learned that in considering this crop protection aspect, that we can modify and adapt always this criteria of diseased units in the leaves by defining what is a diseased, and if we have this clustering of the spots, we can say, okay, a diseased unit is when you define it as 1, 2, 3, 4, 5 cluster. Then you can quantify a leaf as disease. Then you can perform in a determined area the disease incidence. Well, in the discussions, we observe something also additional for the pram, important for the pram breeding, and was that furthered, leaf segmentation parameters, like for example, this disease area on the time can be potential also to differentiate resistance in variety trial. And cleared, we make an experiment with different varieties, and we observe, if we calculate the RDPC, we can differentiate this behavior. And this is actually quite um, clear to describe because when the disease development, the size of the leaves, so is leaves out the root, the sentences come out, the size is reduced, and therefore can be also be used to quantify the disease. This was the explanation. And something interesting, it was also nice to observe that the form how you segment the image, whether a circle or leaves is quite important for a parameter. Here an example, number of cluster didn't have any meaning when we segmentate with circles instances, but when we segmentate this with leaves, it start to make some differentiation between the varieties. So this was also quite important to see how you segment the images can deliver you potential parameters to differentiate varieties. And we also make some simulations of this criteria for defining a diseased leaves or a diseased pathogen, and this is what we wanted to play because we still observe some false positive rate even by segmented the leaves. Here's a curve, for example, when we have one, uh, one cluster defined as a diseased unit, and we observe that even though we have false classification at the beginning of the approach, but when we increase or when we say, okay, define diseased leaves when you have 5 or 15 or 25 spots, then this false positive rate is reduced. Nevertheless, the curve is shifted in the time to the left. Um, and this is for us quite interesting because we are losing somehow sensitivity in the time. And this is a disadvantage if we want to use such an automatic approach for plant protection measures. There is a cost of the false positive rate in that case. To sum up, at that point we can deliver this parameter. Here we see the curve of the experts for disease severity, for disease incidence, and we have a nice similar behavior for disease severity with the automatic approach or the UAV approach, but there is a clear gap of the disease incidence calculated by the drones. And we observed, we can control it somehow. This was our idea that we can reduce or shift the curve into the right in the way that we control this false positive rate, but we still believe, and we didn't this was a hypothesis at that point, that there is a technical gap, and this is probably related with this three-dimensional development of the disease. And nevertheless, we have one important aspect that's we have to consider by monitoring, and this is the spatial aspect. If we quantify one specific point to the field and we find the hotspot or where the disease is located, we don't know how can we our responses we quantify it in a spatial form by subsampling a field in different subregions. And this is what we wanted to test because should be probably interesting. This is what motivated via site-specific application or site-specific control. And this was also the motivation for the demonstrator. And this is what we actually did in year 2022 with the demonstrator here in Göttingen. And the proposal was to use this pipeline that I showed you before, and to adapt this for a site-specific application. And then we release the disease in these red dots, and we use also different fungicide management, a site-specific management, but also a uniform application based on a tractor-based application. And and we also tried to make some statistic. Therefore, was a design on farm, but also wanted to have some levels and some repetitions to make some statistic and differentiate if the fungicide strategy should be better or not that good. Um, we need to integrate pilot mentioned before, and this time by subsampling complete field in different subregions and deliver for each subvariance also an indicator or a disease incidence or a disease quantification parameter. And therefore we adapt by subsampling the field. We increase we put it into this pipeline, the leaf segmentation model, and then later on the pixel classification model, and then later on the post-processing model to deliver these disease quantification parameters. Um, we need an indicator for applied fungicide, and we didn't know, so we start with many basics basic information, and we didn't know. We need to decide at what point we apply the fungicide, and therefore we say, okay, at one disease incidence should be the false positive rate and enough to take a decision for application. And therefore, we say, okay, by 25% disease incidence, we can apply the fungicide. So therefore, we establish our first indicator of fungicide application. Also, we try to perform, as mentioned before, some statistics to understand better how is this spatial distribution by analyzing the different parameters and correlate it with the yield. The results tell us that by considering the distance of every subsample to the inoculated plot, some parameters are important. For example, leaf spacing parameters, and especially disease incidence based on the leaves, but the numbers or cluster based on the leaves are strongly influenced by the distance of this inoculated plot to the subsample point. By observing the fungicide strategy, other parameters are important. And here, again, highlighting the way how you made your images. And here, the circle-based parameters are highly influenced by the area of the healthy tissue, the area of the foliage, but also the foliage cover of the disease region is quite important. Uh, by considering the yield, and these are quietly related, no, circle-based with also circle-based and the ODPC, and they were highly correlated with the yield. Here's an interpolated yield map, and here's our parameter, UAV parameter for foliage cover, and was the parameter that present the highest correlation. Nevertheless, to the yield, we did not observe some influence of the distance from the inoculated point but also no influence of the fungicide management. Yeah, as I mentioned before, no yield penalty was observed by site-specific application, but uh, we probably, and at this year we consume a bit more fungicides than the uniform. And what was the explanation in that case? That we didn't have an indicator for applying fungicide. We already established one threshold for applying fungicide, but it's a time series monitoring. So when we apply the first time, 2 weeks later, after the waiting time for the second application, we observed that again we overcome the same threshold, and we again apply in many site-specific approach. So we came to a more consumer fungicide, and this gives us that more important to establish a second or a third threshold value for the UAV-based approach for applying these fungicides. So this was the message of that point, and the conclusions are quite variant. First, I will start with the conclusions for the pram breeding, and I can say that, yeah, UAV or multispectral system highly recommend for breeding process for the screening of tolerance or resistance in variety tribe. And the explanation or the principal explanation is that you require a high recall and precision value of two objects in the image, and these are the healthy and the soil object. And well, we use multispectral images, and we know that near channels and red channels can quite good segmentate these two objects, and therefore was quite positive for the breeding aspect. We also said that we do not require high resolution. In that case, we could came into the same conclusion with resolutions up to 5 millimeters, which is feasible for multispectral system. Um, For future investigations, we observed that yeah, this require more robustness if we need to apply this approach and breeding programs. You make these tests in different locations, so multi-yeared and multi-locations aspect have to be um, tested in the future, which include probably a constant maintenance of the models and the pilot. Um, yeah, the breeding programs or the breeding progress had different stages, and you start, for example, from the mass selection to the hybrid production. For example, have the experience to work with a mass selection experiment, and here comes really crazy varieties with different colors, different shapes of leaves, and all these aspects have to be considered in a pilot if you want to introduce this into a breeding process. So yeah, these are aspects that have to be worked into the futures. And also one important aspect are the combined abilities. What are combined abilities is that when you see for two traits in one experiment, for example, high resistance, but at the same high yield, so you can adapt your pipeline. This was also one of the principal motivation to take out different parameters to take the chance to take these combined abilities. But this focus have to be taken into mode in a deep. How about the crop protection aspect? So we learned that the standardization of the scoring unit, leaf segmentation, for example, is quite important for that aspect. And the more important message is that the requirement for a crop protection is quite different than the requirement for the plant breeding. And this is more focused in the diseased region of the image. It doesn't matter if you label this by pixel, by bounding box, or by patch image. You require in that case a really high recall and really high precision of the diseased unit. Let's make a simulation. What happens if we have a low diseased low precision of the diseased unit classification? So low precision, you start detecting fast positive units or detecting diseases when the disease was not there. This comes into an incorrect warning signal. So you are misspending fungicide, and in the future this can lead, for example, to the development of pathogen resistance, which can be yeah, catastrophic in that case. If we simulate another case with a low recall or low sensitivity of the pilot, so you are detecting the disease late, so the disease will spread, and this will lead to a yield loss. So quite important for the crop protection to have the best performance for recall and precision, and therefore a pipeline should have the following yeah requirements: high precision, high recall, but also the highest resolution to have the best sensitivity as possible are the yeah optimal conditions for crop protection, and if we wanted to perform a site-specific decision making. So the future investigations, there are many aspects that have to be investigated in the future. Panchromatic technology can gives you a better resolution, should be important for the crop protection aspect. But for this, we need specific and really detailed ground truth, data at this time on the pixel level, but also at the organ level in that case. So a unit-to-unit references should be interesting also to collect and to have. In our experience, we work more for the plot-based level. So maybe this is an aspect have to be considered in the future. If we really want to know, yeah, the specific indicator for fungicide application, so it's required an equivalence between the disease incidence of calculated by the expert and disease incidence calculated by the UAV data. So this is something in information. This equivalence should be quite important to give more accurate warning signals and fungicides and thresholds. Yeah, other aspect that we also observe in the future, we mentioned what should be the minimal region to take a decision, but also how about the buffer zones, and maybe here the complement aspect of the meteorological data here important. Yeah, uh, aspect to cover by our colleagues, for example, from Facundo or from Maurice also. And yeah, probably in the future will also comes for disease quantification online system application. So we have to adapt how we have to see how is the performance for crop protection in that case and how to deliver these parameters. And also, not just leaf diseases are enrolled, so different diseases they have different way to develop, and multi-disease quantification should be also tested in that case. Well, during the PhD, just to sum up, some previous publication was there, but also some cooperations. And with this slide, yeah, I want to thank, I guess, yeah, it takes some minutes. And to thanks the group at the IFSET to PhenoRob to give the chance for the demonstrator, and also different institutions that make a lot of cooperations also in that case. And thank you so much.